Now we're at the end of this short course, and I want to finish on a fun topic, which is how to write fast, high-performance Python code. This at first may seem totally irrelevant to rare event estimation, but think of it this way. To create more accurate Monte Carlo estimators, we need to run our code for longer, increasing the sample sizes we look at, and hence increasing the time it takes to compute. So an increase in our code performance is equivalent to an increase in the accuracy of our rare event probability estimates. I'll take an example from earlier in the class and show you how I'd go about optimizing it to run as fast as possible. The example is to simulate from a Laplace distribution using MCMC. The Laplace PDF is written and plotted here, and our first version of the code to generate MCMC samples is here. This should look very familiar to you by now. The only difference, perhaps, is that I've been a bit lazy and I used a built-in version of the Laplace PDF and stored it in the pi variable. The key element to making our code faster is timing. We can't fix a problem if we don't measure it. Jupyter has a lot of tools to help us in timing, which I'll go over now. Before timing, you'll have to prepare your computer. Enable the high performance mode in your power settings, or equivalently make sure you have disabled any battery saver modes. Also make sure your laptop is plugged into power if you're on a laptop. Modern laptops slow themselves down to save battery and when they get too hot, so keep this in mind before timing any code. The simplest way to measure the time taken to run a line of code in Jupyter is to put %time at the start of the line. Sampling 100 Laplace variables doesn't take long, 26 milliseconds, but we eventually want to sample 1,000,000 or more. If we try to extrapolate this 26 milliseconds to predict the time it'd take to sample 10,000 variables, we get 2.6 seconds. In fact, the actual time it takes is only 1.6 seconds. If we go back to the sample function, we can see that the first few lines are just setting up variables, and the actual work is done inside the for loop. So when R is very large, we would expect the setup time to be negligible in comparison to the time Python will spend inside the for loop. Extrapolating from 10,000 samples, we guess that 1,000,000 samples will take 2.8 minutes to compute. The time function just runs the line of code once, and this is fine when we're calling some big function that takes a while to run, but it's very inaccurate if we ask it to measure something that only takes a fraction of a second. The %timeit function is better for timing very fast events, as it runs the code hundreds or thousands of times and reports on the average speed. This call, which times sample 1, tells us that the setup time inside the sample function only takes 29 microseconds to complete. One of my favorite tools for measuring the performance of some code is the line profiler extension. After loading it into Jupyter, we just need to run this %lprun command. And it tells us the fraction of total time that each line in the sample function took to run. Clearly, the bottleneck of this function is on the 12th line, where we are calculating the Laplace PDF. We can use the %lprun again, but tell it to look inside the Laplace PDF function we have used, which is inside the SciPy package. The function follows a very common pattern that's seen in most functions inside big libraries. The PDF function spends most of its time checking that the arguments we gave it are sensible and valid, and when it finally decides to do some PDF calculation, it calls on line 1749 the _PDF function to do the real work. As this _PDF function only takes 7.4% of the total time, we can see there would be a huge speed boost if we just write our own PDF code. Another tool that's like Line Profiler but more colorful is the heat extension. It's slightly annoying to use since it requires you to put a complete Python program inside one cell, including all necessary import statements. Yet the final result is a great way to visualize the hotspots in our code. This result tells us that the random number generation on lines 15 and 19 are the second slowest part of this algorithm. My favorite tool, however, is the snakeviz extension. It looks at each function we call and every subfunction that function calls and recursively generates a graph showing the time spent in each function that gets called by our code. The third box shows our main sample function, and inside that, the vast majority of time is spent calling the PDF function from SciPy. All these boxes below the PDF function shows how SciPy is wasting its time processing the arguments and checking the data types, etc. If we look closely, we can find the underscore PDF function, which is doing the real work. I usually don't play with these options on the left, and I rarely look at the table that it produces below. Now we have measured the problem, we identify the slowest part of the code and make a single replacement to speed it up. We found earlier that the PDF calculation needs to be done by us, so we write the PDF using NumPy and check that it gives the same values as the previous version. This is important. We don't want the code to give us different values, we just want it to compute the same values faster. Next, we measure the difference in performance between the new and old PDF calculations. We evaluate the PDF on a grid containing 100,000 points and see the new code is 4.6 times faster. Actually, that's a little misleading. If we were calculating the Laplace PDF on 100,000 points at the same time, then our new code will speed things up by a factor of 4.6. But what our MCMC code is actually doing is calculating the Laplace PDF on 1 point and repeating this 100,000 times, or however many R that we've asked for. What I mean is that the code above is vectorized, but in MCMC we can't vectorize this function. So if we run an unvectorized version of the PDF calculation both ways, then we find that we actually improve the speed by a factor of 31. Now, let's put this new PDF code into the sample function. We save the previous version of the sample function inside a variable, then make the new improved sample function. We check that the two different functions are still giving us the same answer. Then we measure the time it takes each to run. The whole sampling is 16 times faster due to this one change. Running the line profiler again, we see that about half of the function is now spent on the random number generation in lines 10 and 14. In fact, we can vectorize these lines by generating all the random variables we'll need up front. The two functions now give different answers, and this is unavoidable as we're taking the random number generator and using it to generate all the normal variables first and then all the uniform variables, as opposed to alternating between generating normals and uniforms. In terms of timing, this vectorization dropped the time from 10 seconds down to 6 seconds. The line profiler tells us that the PDF calculation is again dominating the time spent in the sample function. The PDF code is just calling the absolute value function, which must be very fast to run, and the exponential function, which would be relatively complicated to compute. In fact, we can avoid calculating the exponential function by writing the algorithm in terms of the log PDFs. Here we set log pi to be the logged PDF of the Laplace distribution, and then we accept proposals if the log of a uniform variable is less than the log of the acceptance probability alpha. The ratio in the log alpha becomes a difference, and in fact the log uniform random variables are actually exponentially distributed. Some MCMC texts actually define the metropolis step in terms of exponential random variables and the log probabilities. This function gives us the same output as the last function, but it's almost twice as fast. There's one final speed up to the PDF calculation I can think of, but it's more noticeable when sampling from truncated distributions. So let's look at the speed of sampling Laplace variables which are truncated to be between -1 and 1. This function adds the truncation by including inside the pi variable the checks that the x argument is within the new support. It takes a second to generate 100,000 samples, and the histogram looks as we'd expect. We see that 46% of the proposals have been rejected. Many of these proposals would have fallen outside of the -1, 1 support and would have a PDF value of 0. However, think about how this pi variable would calculate this 0. Say x is -10. Pi of x would first see if x is too small, which it is, and x greater than or equal to 1 would be a 0. Next, it'd check the right endpoint and calculate a 1. And finally, it would go and waste time computing the exponential term, even though it will just be multiplied by 0. Let's instead handle this truncation constraint before calculating any PDFs. This version looks at the new proposals, and if they fall outside of the support, they are rejected immediately, and we go to the next iteration. If the proposal is inside the support, it is valid, and then the PDF calculation goes ahead. These two functions give the same results, but the new one is 3 to 4 times faster. Now I've basically run out of ideas on how to speed up this code just using Python and NumPy tricks. So I'll turn to a very powerful library called number. This takes a function you've written in Python and compiles it to very fast machine code. So you'll get the speed of C even though you're just writing Python. It's like how R people use RCPP to take the slow parts of their code, which is every part since it's R, and then rewrite them in C++. But this is better as we don't need to learn another language. We just need to put a @ngit on the line above our function, and when it is called the very first time, number will compile it so it runs very quickly. At least that's what should happen. Number doesn't support all of Python. The programmers who made number need to go in and write code to support every new thing that NumPy can do. As of today, the brand new random number generators in NumPy aren't yet supported by number. So if we write the sample function to first generate the random numbers, then pass those random numbers into another function, which is number compiled, then we have some better luck. Now when we run sample, nothing crashes. The first call to sample will be quite a bit slower than each subsequent call, as it spends some time doing the compilation step. After it is compiled, though, it's blazingly fast. It passes our check comparing the output with the previous version, and it is 111 times faster than that version. If you want Number to compile your code straight away, instead of the default just-in-time compilation, you need to tell it the kind of arguments that you'll give it and the type of the return value of the function. This is quite tedious, so I don't recommend it. Here, I also wrote a version using the old random number generation, which does work in Number. Overall, it looks quite elegant. Running the new version twice, we see that the slowdown on the first run has disappeared. And comparing to the previous version, it's a little bit slower, but perhaps you'd prefer this cleaner version than the one that I made earlier. The histogram shows us this is really working as we'd like. Some final thoughts. Improvements to your algorithm and your choice of hyperparameters is usually a better way to spend your time than on thinking about this kind of stuff. For example, if you were running a crude Monte Carlo with 10 to the power of 10 samples and it's taking a week, you should just change to run importance sampling or one of the other algorithms we've looked at, rather than making sure Python is running that crude algorithm as fast as it can. Even with this example, MCMC sampling, we would be better off choosing a better jump size so that we accept the optimal number of proposals and therefore don't need to sample quite so much. One other minor thing to note is that the libraries you're running are getting updated all the time. Updates can be a double-edged sword, but I'm usually trying to run on the latest versions of NumPy and the other main libraries like this. Just the other day, I opened my emails and saw that the new NumPy version made random number generation faster. So I opened up some CMC code I had, which took 5 minutes to run, updated to the new NumPy, and then it took 4 minutes. Not a massive difference, but it took no brain power on my part, so I can't complain. This is the last video of this 2020 Rare Events short course. I hope you enjoyed it and learned a lot of practical skills, even if you don't end up using them to estimate rare event probabilities in the future. Au revoir.